Hello. Today we'll be recreating the in-class example of an elastic and inelastic object hitting a door. Unlike the in-class example, we'll be focusing on linear and angular momentum. We'll address the differences between these two scenarios and use the data to estimate the mass of the door.
We know that linear and angular momentum are both always conserved, but are conserved as separate entities. This ball is coming in to hit this door with the momentum p naught, and thus this door will have an increase in linear momentum. However, because it is attached to the wall, this momentum goes into the wall and the door does not go anywhere linearly. However, because of this ball's movement, this ball's momentum more specifically, in relation to this center of rotation, this ball has angular momentum of L naught. This would be the cross product between its linear momentum, p naught, and the radius of this door. And thus, the direction of this linear momentum is downward. And so when it hits the door, it increases the door's angular momentum downward, which, according to our right-hand rule, will cause the door to rotate in this direction.
So looking first at our elastic collision, we know we have a volleyball with an initial momentum, P naught, in this direction, and an initial L naught angular momentum into the board as deduced using our right-hand rule. So as the ball travels this way with a positive velocity, it'll make contact with the door, elastically collide, and shoot off in this direction. We know in the system that momentum is conserved. We know that when the ball makes contact with the door, it'll transfer its linear momentum, but since the door is hinged, the door will not have any linear momentum. It also transfers its angular momentum, and in this case, the door will end up swinging this way. To find the actual angular momentum of the door, we can use this idea of the conservation of angular momentum. So we know L naught, in this case, the original angular momentum of the volleyball, is equal to the sum of the angular momentum of the ball and the door. And as the ball hits the door and elastically shoots off in this direction, we know that the angular momentum is in the opposite direction as it was previously because the velocity has switched direction. It is negative now. So to find the angular momentum of the door, we can use this idea where it is going to be the difference of the original L naught of the volleyball minus the angular momentum of the ball after the collision.
Before testing, we first found that the mass of the volleyball was about 0.272 kilograms, and that the radius of the circle that the door would be turning in was about 0.7 meters. After taking our videos, we found that the velocity of the volleyball when we threw it was about 9 meters per second, and that it hit about 0.5 meters from the hinges, and caused the door to have an angular velocity of about 0.35 radians per second. Using these numbers and following the equations that Carter just talked about, we ended up finding that the mass of the door was about 43 kilograms with the elastic test. For our inelastic collision, we had a clay ball moving towards the door with an initial momentum P naught and an initial angular momentum L naught into the board. As it travels this way, it will make contact with the door and it will stick to it, causing it to be at a certain radius on the door after sticking. As we know that angular momentum is conserved, L naught will be equal to the angular momentum of the ball plus the door, as the ball is stuck to the door at the end. And when we look to it more in depth, we know that the mass times the velocity times the perpendicular radius, right, L naught, of the ball originally will be equal to the moment of inertia of the door plus the moment of inertia of the ball times their omega. For this test, we already knew that the radius of the door was about 0.7 meters, and we measured that the mass of the clay ball was about 0.23 kilograms. Once we did our videos, we found that the velocity of the clay ball when thrown was about 8.4 meters per second, and that it hit about 0.43 meters from the hinges, giving the door an angular velocity of about 0.143 radians per second. By plugging these into our formulas, we found that the mass of the door was about 34 kilograms, which, although different from our inelastic test, can largely be attributed to the slow frame rate of our phones, possibly giving us miscalculations on our measurements.